Hi. So, okay.
Okay, so today, some of you may have been at the intro presentation yesterday, but again, I'm Jakub, and I'm leading the Picoballoon project, and Sinan is leading the German team, and he's also an electrical engineer in the team, and together today we will teach you how to use the basic features of Eagle. So Sinan will do the first part, which will be about creating a schematic and basically creating a schematic. So Sinan, you can go on.
Hi, I'm Sinan Akkoyun, and as Jakub said, I will do the first part of the workshop, and I will show you how to open Eagle, how to set up a new project, and how to do the schematic. And later on, Jakub will show you how to turn the schematic into a board. Okay. I will start to share my screen. Okay, can you all see my screen?
Yes, we can do. I can do, so I think.
Yeah, me too.
Okay, great. Is the text readable, or is it like too low resolution?
It's fine.
Okay. I just noticed I have it in German, but like the layout should be the same in the English version of Eagle. Okay. So Eagle is built up like that you have projects, and then inside the projects you have board and schematic files. So the first thing we are going to do is start a new project. You do that by clicking File or Datei in German, then clicking New, and then do a new project. Okay, I will call the project Picoballoon Workshop. You can call it however you want. Okay, so now you see the green dot? That represents that the project is active. Oh, I just deactivated. Hold on, here. If you click the dot, you can activate the project and select it in Eagle. And now we want to do a schematic. So we just do a right click, then click New, and do schematic or Schaltplan. Okay. So everybody that wants to follow, are you on the same page as me right now?
Yeah, maybe we can do polls for this, or the people should be able to speak as well. Or you can just write it in the chat if there's a problem. Yeah. Okay, seems that everyone is fine.
Okay, great. So as you might have guessed, in Eagle, there's the concept of libraries, just like in programming. So these libraries you can import different symbols and different schematics, different schematic parts, so to speak, components, and you can import different footprints. Basic principle of a schematic is that you have a symbolic representation of your component. For example, if you have a resistor, you have some symbol that represents the resistor. And then there's the second part to it where you do the actual board, and that's called the footprint. So every component holds a footprint that defines how to do the PCB layout. But Jakub is going to tell you about that later on. So the first thing we have to do is import our library, so we have all the parts there. For that, we can click on Library or Bibliothek, and then Open Library Manager. So are you with me there? Can you please write it in the chat? Okay, fine. So this is the Library Manager, and inside the Library Manager you see which libraries are in the design incorporated, and which are in use, and which are in general available. I have many libraries because I imported them beforehand, and Jakub did you the favor of extracting the parts that we need. So you all clicked on the link that Jakub provided. So I'll show you that. Here is the Google Drive, and here we have the workshop.lbr. ABR obviously stands for library. So we wanna download that. There we have it. I think you already have it downloaded. Okay, so now it's in my download folder. You can move it wherever you want. Excuse me?
So.
Hello? Excuse me, you just talked there?
I'm not sure where it's coming from exactly.
So you heard it too? Okay.
Yes, but you are the only person with an enabled microphone, so...
Okay, however, never mind. So this is a quick look into the library file. It's like pretty cryptic, so we don't have to deal about that, but basically here are some... Oh, I can hear it again. Hello, who is talking? Could you please mute your mic? Okay. For example, here we have just some positions. I'm not going to go into the details because we don't really need them. But like, it's a normal library file. So, okay, we will go to our schematic again. You probably have the Library Manager open right now. And now click on Available, and you can browse the libraries. So now, if you have that window open, head to your download location and open the workshop.lbr. It could take a minute if your PC is slow. Okay, so do you all have that? Could you please write in the chat? And please write in the chat if I'm asking too much, and you can just follow along. Okay. Okay, Samuel, we will wait for you. Okay, great. So now we have the library installed here. And now we can just search for workshop. There it is. Now you can click on it. And for every library you have available, you can use it. That's so if you do a new project and you have a different library set, you don't just merge every library set you have. So it's for having it clean. So now click the Use button. Okay. So if that's done, you should see the workshop in the In Use category here. Okay. You could remove it, you could edit it, you could do many things, but this is the gist of it. That's everything we have to worry about for now. So now we can close the Library Manager. And if everybody gives me a quick text, if everything works out, we can go ahead and start the design. Yeah?
I realized that I didn't put the frame component there, which is just for the schematic, but everyone should have that defaultly in their ego.
Also, the frame is a default component or what?
Yeah, it should be there when you Google, just Google search frame and the components.
Okay, I will try. I will try.
Okay.
Thank you for that. Okay, so is everybody good? Can we start doing the schematic? Samuel says yes. Veronica says yes. Okay, Kevin, what about you? Hello, Kevin. Excuse me. Are you fine? And can we start building the schematic? Okay, no answer there. I will just wait a second. Okay, you're not answering, so I think we can start designing the schematic. Okay, great. On the left-hand side, you can see our toolbar. It's like in Paint or Photoshop or any program, you know. Here you have some basic tools. The most basic one is the net tool. It's the green L that's laying on the side. The net tool basically is like putting wires in your schematic. So if I just select the net tool, click on it once, then do a left click on the canvas, I can now draw a net. This is not really useful without components, but I will show you that. But to keep in mind is that if you draw the component, if you draw the net and want to end the net, you have to press escape. And then the last point you clicked is the last point where the net ends. Oh yeah, Jakub told me that I should show you how to turn on the grid. So on the top left corner, you can see something called the grid or raster in Germany. If you click that, you can put a grid on your canvas. And so this is especially useful for big projects where you want to keep like a symmetry or want to keep the schematic clean. Here you can choose some parameters, like you can put there whatever you want. The grid is especially important for the board layout. The dimensions are really important for the board layout, but like for now we can just press OK.
You can set it the display option to on.
Oh yeah, I'll show. Thank you. Okay, yeah, you have to put the display option on, like Jakub said, in order for it to function. Okay, now it's on. Okay, great. So now you all can see the grid, and it's much easier working with the grid. Okay, here are some basic tools. Starting from the top, you have the group tool. The group tool is kind of like a selection box. You see, if I left click and drag across the whole net I just drew, I selected it. Now, based on the group selection, we can do some manipulation of the objects, like move, mirror, rotate. We can do everything. We just select move for now. Now I can move parts of the net, or if I select the group beforehand. Yeah, okay. Never mind. I will show it to you on the components. So for now, we will just select it with the group and press delete on the top right of your keyboard. Okay, now we deleted the net I just drew. Let's start with components, and then I will show you the basic tools. So here is the add component button. You just have to click it. And then the add dialog opens up. here in that dialog, you can search for your parts. I have quite some libraries installed here from SparkFun and from Eagle, and you also should have the ones from Eagle too. Okay, so I will show you an example of what we're going to do. This is the schematic we're going to build. And for the first thing, we want to add a frame. So everything looks tidy, and we can put like stuff there, information that's kind of important if you're working for an organization or at an international student project like the Picoballoon. Okay, so to add a frame, you just type frame in here. Now we have many kinds of frames to select from. You can see they all have their purpose. Yeah, you can choose whatever you want. If you're working like in a big group, you should, like for example, we are using A4 log, this one, and that's kind of a standard frame. So we'll just use that, click the A4 log, and then press OK. Now we have the frame here selected, and now with left click we can place it. Okay, great. Now you see we're still in the placement mode. So to exit the placement mode, we just press Escape and close that. Okay, now we're out of the placement mode, and we can start placing our components inside the grid. So to do that, we click Add Part, just as before. And now we are starting to search for our microcontroller we want to start with. So basically, we are building an Arduino ripoff, kind of. The Arduino uses the Atmega 328P, and that's the same chip we are going to use. So, okay.
Maybe just try to manually look it up in the workshop.
Yeah, I will do that. Okay, like just as in the file explorer of Windows, you can sort for different. You can sort by the alphabet for different attributes. So what I just did there is click on the managed folder, and then it's kind of sorted from the managed folder names for alphabet. Okay, now we have here the workshop. You should have that too. I will expand the view and then choose the Atmega 328P. Are you all on the same page right now? Can you please text that to me? Okay, Veronica says yes. Samuel says yes. Okay, and I think Kevin won't reply. Okay. So just click that Atmega 328P and press OK. Now we have our component here. We will just place it in the middle of the schematic. And now let's take a look at it. So just give me a second. So the thing I told you about schematics and footprints, this is the exact same situation. You can see here, we can just Google for Atmega 328P pinout. I will open that in a new tab. Oh, hold on, that was the wrong thing. So, if you see that, that represents kind of the footprint, because that's the actual chip you hold in your hand and you solder on the PCB. But as of right, as you can see here, that's not representing the footprint, the actual physical footprint of the IC. This is just a symbolic representation for the schematics. And this is really cool. You can see all the pinouts here. You can see all the pins, starting from VCC to ground. I will explain what that means later. And yeah, we won't have to deal with pinouts in Eagle because these are already built into the footprint and stuff like that. You will see what I mean later. Okay. So the thing about Arduinos is that, of course, they need supply power. Here, the pin VCC stands for power input, so to speak. The 3 to 8P has a specific voltage range we can work with. And in this case, we will not specify the voltage, but we will put a VCC component in there that will tell us later which pins we should connect. So just open the edit the add panel and search for VCC. And as you see, we have in the workshop, we have the VCC component. We will just click VCC, click OK, and add it somewhere here. Okay. So basic wiring goes like that. You choose the net tool, click on one end of the pin, then click on the other pin, and then you're done. We just connected the VCC net to the VCC pin. And this symbol here, right here, is kind of a, it's like a collective connection. Like if I place another VCC component here and connect that to some other pin, like that's just an example, like here. That's not right. It's just to show you. These two are connected in the final PCB layout. This is for convenience sake and stuff like that. So I will just, oops. I will just select the VCC component and delete it. Okay. So let's just do the same thing with the ground. The ground is like the minus pin of the power supply. Ground is, the short for ground is GND. And now we just select the GND component here, press OK, and connect it here. Connect it with the net tool. All right. Great. Just like if we want to move the ground thing to another place, we have to look at where the origin of the component is. So Eagle works the way that, I don't know, I hope you can see the little cross here. That's in the middle of the component. And if we click that, we select the whole component. So that's basically the origin of the schematic symbol. Okay, sorry for the bad Windows sounds. The thing is, we don't, so for now, we supplied VCC and ground to our IC. But that's not all we have to do. We have to do much more to get the ATmega working. So if you take a look at, for example, online documentations about how to do a minimal circuit for the ATmega, like just like that. We can see that, like, for example, open some link. We can see some schematics of different designs that people do with the ATmega. The ATmega is a well-known microprocessor, so there's much documentation and many schematics of it. Based on the minimal layout we have to do, we will just follow along the layout we did, and I will explain you the components. So just give me a second there. Okay, great. So, the thing we want to add right now is some kind of reset circuitry. So you can see here the PC6 pin, there it says reset. The thing with resets is that if you want to program your microcontroller, you have to reset it first, or if you want to rerun the whole microcontroller firmware, you have to reset it. Oh, just give me a second, I will hook up my laptop to the power supply. Okay, so the thing is, ich war hier gerade in der Workshop. That's good. Okay, Jakub just told me we do the fancy stuff first. Okay, So power supplies are not that clean as you might think. If you, for example, take a DC to DC converter, hook it up to a battery, and use the raw output like we are doing here, it could potentially damage the IC with like voltage spikes, or it could just run it unstable. So to fix that, we add some capacitors. To do that, we click the Add part, delete our search query, and then we will just click on the Manage Folders or Workshop folders at the top there, expand it, and now we have some capacitors here. Okay, these are 0.1 microfarads, like that's the capacity of the capacitor. And as you can see, we can not only choose the symbol, like you can see the symbol is all the same for all the components, but now we are like by expanding the symbol, the component, we can select the footprint. You can see the footprint here. Like there's some basic descriptions of SMD package footprints. We will talk about that later. Just for now, we will select the 06031 ones. And Jakub, can you please tell me which ones of the 06031 ones?
Oh yeah, sorry. All of the decoupling ones are 0603, 5%.
5%, okay, thank you. So we will just choose the 5% one and then press OK. Now we have a component here. The thing with components is like that, we maybe don't want to connect it this way, we maybe want to rotate it. So while still at your mouse pointer, you can do the right click, and with the right click you can rotate your component. As you can see up here, it changes the orientation as I press right click. You can also do that with the rotate tool, but that's more convenient if you do it while placing the components. Okay, so let me just see where we place the first decoupling capacitor. Okay, we'll place the first one here. Okay, just like that. Now we have our component here. It's connected to here, and as you can see, here's a little dot, and that dot just means that traces are connected. If I just do a natural right here, you can see these are not connected. Like it looks like they're connected, but on schematics, these are not. These are connected when you do a junction. The junction tool is right below the net tool. So you can click on that, and now you can see a warning of integrating nets into each other. You can see Eagle just put an arbitrary net to the line I just drew. And now it asks me if I want to connect that into the VCC net. I press yes, and now I have a junction. This you don't have to follow, that was just to show you what a junction is. Now I select the nets and press delete. Okay, so let's wire up the decoupling capacitor. To do that, we will take the GND component. You can just Control-C, Control-V the component after you selected it. You can also use the copy and paste buttons here. I just did that with the shortcuts you all, I think, already know. Now you place the GND, and now you choose the net, and we connect the capacitor to the GND. Okay, so just some basic knowledge. Why is this capacitor needed? If we connect an unclean power supply, like to the VCC and ground, like I just told you, it could be that we could get voltage spikes in the output. So because of different phenomena, we could actually maybe kill our microprocessor or have dips because like sometimes the microprocessor needs much power for some clocks, and it's not always able to get the high current draw from the power supply if it's weak. So we add the capacitor. The capacitor charges up with energy, And if the microprocessor needs the power, the capacitor can just discharge into the microprocessor. The capacitor can just discharge into the microprocessor, and we eliminate spikes. So the thing with microprocessors is that there are different internal routings. Like the VCC is for the digital IOs. So IO stands for input outputs, as you might know. And the VCC is connected to all the digital pins. But the thing is, we also have analog pins on our microcontroller, like the ADC. ADC stands for analog to digital converter. And these pins can basically take a given voltage inside a given range and convert it to signals the microcontroller can understand. So for example, if we would connect here a 2-volt power supply, and our main power supply is, for example, 5 volts or something like that, we could write a code that monitors the 2 volts on this pin because it can sense analog voltage. But in order for that to function, you need to power the analog circuitry inside the microcontroller, and you have to give it a reference voltage. The reference voltage is just there so it absolutely knows which voltage it senses. To do that, we will just connect the AVCC to our VCC net, just like that. And now, for good practice, we add another decoupling capacitor that will also decouple the currents and voltages of the AVCC supply net. I will just move that here, so we have some space to work with. Yes, we want that. Okay. Now we can just move the component here, choose the net tool, and connect it there. As you can see, as we also know, these two traces are not directly connected. Like they are, but just looking at the schematic, they are not, because there's not a junction. Okay, we can just tidy that up by just moving this component here, deleting this line, just doing another net here. Now it looks much cleaner. And we also have to connect the ground to the capacitor. Just like that. Okay, just a reference. Can everybody follow me, or are there some questions you guys have regarding the microcontroller situation or the decoupling? Okay, we will just wait for Samuel. Okay, for Veronica, everything is fine, great. Okay. So, Samuel, do you need some time? Okay, perfect. So, we just supplied our chip with power. I will just connect the reference voltage there. Just so we take the part. Copy it. Oops, that was wrong. Take the part. Okay, copying doesn't work. I will just add it right here. Take another capacitor. Put it here to the AREF. That's for analog reference. Get the net tool. Connect it there. And now we will paste the ground component or add it through the add page. And we'll connect the capacitor here. Okay.
Yeah.
So Sinan connected the analog reference right now, and so this, as he said a while before, it's a reference for the analog pins to measure the voltage correctly. So if you have a stable voltage reference, if you have stable voltage reference from the outside, you can connect it there and you will have an external reference. But if you don't have a source that you can rely on, the Arduino has, this chip has an internal reference, which creates a voltage by itself. It's not really very, very precise, but sometimes you cannot have anything else from the outside, anything better. So in that case, you just put a capacitor there, so it's stabler.
Okay, thank you very much. Okay, great. So we just powered our microprocessor up. This is the minimal circuit we have to do, because it's just supplying. Oh, yeah, well, if the chip is programmed, this would be the minimal circuit. But of course, we want to program it and do stuff with it. So we will just connect the reset pin here. As you can see, all the pins are normal except for the reset pin. This circle right here shows that the input is inverted. That's also the deal with this slash here. So basically, or in datasheets, you can see a line on top of the word or on top of the pin that just tells you, hey, the input is inverted. That means, like, I would just wire it up and then explain it to you. So we will take a capacitor, just as before, to decouple it again. This is for a good practice. So we just have our capacitor here. Now we will connect it to the reset. I will just move the VCC down so it's better visible. Okay. So the thing is, we not only have pins and nets, we also have labels. If I pull out a net here, press escape, so I just drew the net, we can do labels here. Labels are like these VCC components here. They specify a specific net, and labels are especially important if you have big circuits where you have much stuff connected and you don't want 1,000 traces or wires to cross each other. That's when nets come in handy. So we will just place a net here, a label I mean, click on the wire, then put our text where we want it. Or we can choose the type of label here up here. Either we want to just label the net, or we want to do a new label. I want to do a new label. I rotate it like I want. I bring it to the net, click left click. Now I placed a net label. Okay, so we want to edit the net label name. So what we will do is choose the name tool. We'll just click on the name tool, click on our label, and we click on the net, I mean, and now we name the net. For example, I will name it BTR. I will explain that in a second. Then we press OK. And as you can see, we successfully put a DTR net label at here. So basically, if we were to do something new, like here, and connect something there, and we don't want wires to cross, I could also label this. Okay, choose the name tool, label this net, also BTR. Now it asks us if we want to connect this net with this net, and that's the basic concept of nets, that you can connect these. now this is connected to there without having a visual connection directly. I will just delete that because that was for presentation purpose. So the thing is, I told you the reset pin is inverted. What that means is if there's a digital voltage of 0, like 0 volts or below some threshold, the reset will start. And if the voltage is high, so like 5 volts, for example, the reset will not occur. This is because it's inverted. If it weren't inverted, and if the slash weren't there and the circle weren't there, it would be the other way around. Like we would connect ground to it, so it wouldn't reset, and then 5 volts would reset. But because it's inverted, we do the opposite. So now we will do something that's really important in microcontroller circuits and circuits in general. We will do what's called a pull-up. Okay. To do a pull-up, we need a pull-up resistor. Just open the add context. Now we would see we have resistors here. That's the schematic symbol for resistor. We expand the view. And now choose our resistor. We want to pull up there. So I will just have to ask Jakub, which package did you choose for the resistor to pull up?
Yeah, nah, that was the axial.
The axial.
First one.
Okay, great. So we will choose an axial component here. Jakub will show you what these components look like later when we do the board. We are just for now concerned with the schematic. We click it, the first run. We will press OK. We will rotate it here, place it here, escape twice. So, and now we want to connect this to VCC. So I will just add a new component, search for VCC, or do it like here. Choose it. Oops, okay, choose it, then connect it. You can also connect things directly. This is not as tidy as one would think. I will move it up there so we just see the green net. Okay, great. So basically, as I told you, because the input is inverted, the pull-up resistor, kinda like the name implies, pulls the voltage up. So it's plus 5 volt every time. So the microprocessor gets a digital high as the input. So, and if we connect this DTR to ground or to minus, so to speak, then we like electricity takes the path of least amount of resistance. Like that's not the whole story, but it suits our purposes here. We connect this to ground, then we will pull that low. We will pull the pin low.
Sinan, there's a suggestion in the chat.
Oh, okay, hold on. What about an intermediate saving of your work? Oh yeah, sure.
Yeah, Eagle is not very good with this. Yeah, some other programs in this category do save automatically, but if Eagle crashes, which is not so often, but it happens, you many times can lose work.
Yeah, we will just save our work here. Press save. And we will name it schematic or whatever you want, .sch. Okay. Yeah, if we just do if we move that component and we want to save it again, we just press Control S. Now it's saved. Okay, great. Thanks for the recommendation. I almost forgot that, or I forgot that. So, okay. This is the absolute minimum we would have to power the circuit and reset it. The thing with microcontrollers is, hold on. Okay. So the thing with microcontrollers is that they have they operate in a clock system. So every x times per second, an operation is done, and for that, you have oscillators and crystals, electrical components that will tell the microcontroller, that will give the microcontroller a time frame. So the Arduino has a built-in oscillator That's fairly accurate. I think it's in the 10% margin. And that's great for some projects, like for the Picoballoon, it's great. But just for good practice, we will put an oscillator here. So the Xtel pins are for the crystal to connect.
Yeah, so also I would say that the problem is that to enable the this oscillator, you need to do some pretty complicated processes. And if we make this board, you can really you can order it, manufacture it, and it's much easier to do it with an oscillator there.
Oh yeah, sure. Yeah, exactly. Okay. So we will add a part. Set query. For workshop, expand it, and we will go to crystal. Okay, now we have many crystal components here, or so to speak, many footprints of a crystal. We will search through them, and I think we will add this one. Am I right, Jakub?
Yeah, that's fine.
Okay, so we will take this one, place it here, and now we will connect it. But this is not the whole story. We also have to connect some capacitors. And that's just so the crystal can oscillate. So we will do a...
yeah, there is not a universal capacitor, okay, but you can just add the big one, the last one, and then change the value.
Okay, we'll do that. Okay, we will just take this one, and I will show the concept values. So I will place them like that, so we can see the values and names. Now I will connect this to here, and this to here, and I will tie these to ground. So tie this to ground. Yes, we want to integrate that. Awesome. Now we just did the oscillator part, and we have to change the values because the oscillator doesn't want to oscillate with capacitors of a big size of 0.1 microfarads. So we will choose the value tool. Excuse me? Who has the microphone unmuted?
Yeah, sorry, that was me.
Okay, fine. We will take the value tool, click on the component. Now we just press yes, and we want to change the value to 22 picofarads. We will do the same for the other capacitor. Okay, nice. We're done here. So just give me a second. Okay. Now we will add the programming lines. We do that by pulling out the RxD and TXD. Basically, these pins are mandatory for a protocol called UART. The UART protocol is a serial communication protocol where we can talk to the microcontroller with our PC or some serial console. After resetting, we can program the microcontroller through the RX and TX pins. RX stands for receive and TX stands for transmit. We will just break that out with some labels, like that, and like that. I'll move them apart a bit. Okay, I personally don't like these lines like that, so
you can resize them through the info tool to 0.05, and that way they will.
Just hold on.
You click on the net. Yeah, like that.
Oh yeah, that's the size. Okay. One okay? Yeah, I will take the one. Okay, great. Thank you very much. We'll do that with this one too. We take the info tool up here, click on the label, and then change the size. Yeah, awesome. Okay, now I'll take the name tool and name them accordingly. this one the RXD, this one the TXD, just like on the symbol. Okay, so just 2 steps ahead and we are finished. The thing is, we somehow, if we design a PCB, we want to have a connector where we can interface with our microcontroller. We currently don't have that, we just have labels, and labels do not represent some kind of connector. For that, we will place a header. For that, you click the Add Component part, look in the workshop, and here is the connector. Okay, you can choose all kinds of connectors. We, for example, want a 6-pin connector. These are all 6 pins, conveniently. We could choose all kinds of connectors. I think, Jakub, what do you have in mind? Which one do we want to use?
It's the down below the 06 SMD female V2.
Oh, okay, we do an SMD connector. Okay, sure. Okay, we will click the part, select it. Press OK. Now we will place our connector right about. I will place it here. Okay. So now we can connect our pins to the header. There's kind of a basic layout system that programmers use, or like serial to UART programmers, so to speak. So we will connect 1 and 2. Connect this to G and D. If I'm going too fast, just type it in the chat, please. Connect the G and D, or ground, to our header. Okay. So now we want to connect the VCC. So we can supply some power through the header. Connect that to pin 3. Now we're connecting the TX and RX. So I will just pull them out here. Here and here. And this one is for reset. We will place our labels here, here, and here. Rename them. So pin 4 is corresponsible for the TX, for the RXD line. I'm sorry, for the RXD. I'm sorry. Yeah, like that. And the other one is for the TXD. And last one is for the DTR. DTR is just a naming convention for like the reset pin for UART programmers. So we will take the info tool, scale them down to 1 because it looks great. Just looking for we will take this one too. So we're consistent, we will scale everything to 1. Do this with this one too. Okay, awesome. So now we just broke out the header. But our board is pretty boring right now. It doesn't do anything. So we will add peripherals. Peripherals stands for like anything almost, like adding sensors, adding LEDs, adding input-output devices, adding a keyboard, stuff like that. We will connect an LED to the pin PB1. To do that, we will open the add context, choose the LED, and then we will choose the 5mm LED because that's pretty standard and common. Take that, press OK. Now we will orient it like we have to. So the thing with LEDs or diodes is this side is the anode and this side is the cathode. So what it means is here it connects to minus and here it connects to plus, or ground and VCC. And the microcontroller, through its I/O pins, can supply power, of course. So we will connect the LED plus or anode to our microcontroller pin. The thing with diodes is that they have a current limit, so just a specific amount of current should be able to flow through the diode, otherwise it would break. So to limit the current, we will place a resistor, because the resistor resists against the current. So to do that, we will just open the Add menu and choose this 0603 resistor. Press OK. Put it there.
It was the axial originally, but it doesn't matter.
What do you say?
It was the axial originally, but it doesn't really matter.
Yeah, then I will do the axial. Okay. Take the delete tool, delete that. Take the move tool, move that down here. Okay, and connect the whole thing to ground. Great, now we will just assign some values, because we didn't assign a value here to the reset pin and not to the current limiting pin. There are online calculators for calculating the LED current and the LED resistor. We will just take the value of 300 ohms. Okay, so we put the 300 or 300R here, the 300, and now we will add. We will give this one a specific value. So for pull-up pins, we don't want much current to flow, because we don't want our circuit to waste power, and we certainly don't want to directly connect it. So the pull-up resistor value for our example is 10 kilo ohms. That's 10,000 ohms. So our circuit will not draw much current when operating. Okay, great. We're basically finished with the whole schematic. It looks kind of funky, and that's the basic schematic you can do within AddMega. We just added a peripheral, like an LED here with current limiting resistor. We added a breakout header that you will see on the board, and we added many decoupling capacitors and crystal and the pull-up line for the reset pin. Okay, great. We will do a quick pause right here. And after the pause, Jakub is going to show you how to actually design the good stuff, that is the boards, how to route boards, and then you will get a grasp of how it will look in real life. Thank you very much.
Yeah, so we talk again in 5 minutes, so that's 3:10.
Okay. So everybody could follow along, right?
Yeah.
Okay, great.
Because it was a lot of stuff to take in the past hour, and it's going to be another stuff.
Yeah, okay, great. And we will see us.
Okay, so breaks over. Can you see my screen? Okay, great. So my schematic is a bit differently arranged, but as you can see, but the electrical connections are really the same. So we can start from here. Well, so you have the schematic, and now to create a board, you will need to switch to the board view. So you do that with the button here, and you just generate switch to board. It gives you this prompt, and you just select yes, and you are greeted with this nice new window. So does everybody have that loaded up successfully? Okay, so there's a lot of different stuff to look at here. You have a lot of similarities, mainly in the tools, so you are already familiar with these tools. You have a lot of new tools here, also some old stuff here. Yeah, so at the board design is based, you don't have symbols anymore. You have physical representations of components in some scale. So these are the components you would put on the PCB. So now, yeah, we want to show pictures of the components? Well, maybe. But Sinan already showed you before the picture of an Arduino. So you've seen the large black rectangle, that's the microcontroller, and maybe later on. So the first important thing maybe I would show you is the grid. So you already know that from the symbol view, or yeah, the schematic view. But here it's even more important, because when you are working with the physical stuff with some physical dimensions, so it's good to keep track of how it's arranged and what scale. So we normally use a millimeter scale for this, while the previous one used inches. So I have 1 millimeter of this normal scale, but also when you are working with the board, you many times need different scales. So I also set this to millimeters, and I put, for example, quart or maybe tenth of a millimeter for now. And so what this means, it's behind the alt tag. So now I have a millimeter grid, but when I can move stuff a millimeter in each direction, but when I press alt, I can move stuff around tenth of a millimeter, which is nice if I need some additional precision. Now I just return to the original position, and also you can see that the stuff is misaligned because originally it was the inch grid. So what we can do now, because it's really bad to have stuff not aligned, we just select everything with the group tool you should be already familiar with. And here is a new tool called Align. So you just press Align and Align to Grid. So now everything is perfectly at the grid. So you can see the different components. Here is the microcontroller. Here are some of the resistors. You can see them by their names. So R are resistors, C are capacitors. And now we will need to start laying them out somehow. So this is the layout process. I would also delete this thing is the board. So this is the actual physical size of the board. When I would manufacture this, there would be a drill bit going here, and cutting out this piece of the board. But I want to just not have it here for now. So also an important thing which you might have seen in the schematic view, but is more important here, is the origin point. So this is like you have a coordinate map, and this is the x0, y0. So here everything starts. So the largest component, and everything needs to go around with it, is the microcontroller. So I would first place that. Let's say like this. And there's a lot of different ways you can arrange components. There are some rules I will explain, but there is not a single correct way to do this. And since we don't have so much time, I'll just show you the one we did. So first of all, let's check the orientation. Yeah, so it's rotated like this. And the first thing, which is pretty large, I would add it, is the oscillator. So now I can have it like this. And an important thing to remember with oscillators is that the traces going, so I'll explain it what a trace is. Basically a cable. So here is going to be a cable connecting these two components. So the traces need to be as uniform. So now you can see a bunch of these components, and you have these yellow lines, and you probably already figured out that the yellow lines represent what needs to be connected. So now we can lay out the other steps. So here are the capacitors. You can connect them like this. So now this is not a straight line, so you can also, I'll move this just a bit away. Now this is not a straight line, so you can just press Alt, which gives you the smaller grid, and you can align it much more precisely, like this. And we do the same with the other one. So now it's very aligned. Does everyone have this? Great. So let's move on. And what else do we have? So maybe here are the capacitors. So the point, these two are for. So these two are for stabilizing the spikes, as Sinan explained previously. This one is for the analog reference, which I explained, and this is for the reset line. So we can firstly place the coupling ones, or block capacitors they are called. So these should be as close to the voltage line as possible. And you can see that even though I'm really close to it, these yellow lines still are going somewhere else. So what you can do when you have something like this, you can look for a tool called RatNest. So what this does, like if we zoom out, a RatNest tool finds the shortest direct path between the 2 points that need to be connected, and it just redraws the yellow line. So if I click that, you can see that they reorganize. And now when I have the VCC is going directly to this pin. So it's there. So you also have similar tools here, like you have move, rotate, but here, since you will be doing a lot of moving, rotating, and
Oh, I'm sorry, Jakub. Samuel can't see your screen.
That's weird. And the other people can see it?
It just stopped, he says.
Yeah, but can you use it, for example?
I can see it, and I think that's intentional that he has zoomed on the C8. If that's your problem, Samuel. I just wanted to add that the importance of line traces of the oscillator. Like Jakub just placed the oscillator pretty near to the at mega, because if you draw traces, every trace like makes capacitors on its own. Like you could theoretically do a PCB without components and do traces and loops, so theoretical capacitors occur, and that's prevented with having short trace lengths, so the oscillator can swing good. That's everything I wanted to say.
Yeah, thanks for that. Maybe Samuel, you can try. I mean, it's supposed to be zoomed. Like now, it's not zoomed, right? Well, then maybe you can just close the room window and try to reopen it. You should be able to get here again. So, yeah. Now, what do we have? So, yeah. Now I'll show you some quick shortcuts on moving the stuff around. So normally you just click on the component, you can move it. When you want to rotate it, you should have a mouse. I hope that everyone has a mouse. Without the mouse, it's really complicated, but you can do it with a touchpad. So with the mouse wheel button, so that's how I move around, you just zoom in and zoom out. And then when you move it, you can press the right mouse button to rotate the component. And you can also press the middle mouse button, so press the wheel, and it switches to the other side. So I will explain what the other side means in a bit. Now you can just keep it this way. So I will align it with this thing, put it close, like this. I mean, the lines don't need to be perfectly straight. It's just, it depends on how much time and how much OCD you have to do this. So something like this. We do the same for the other side, because when you have these decoupling capacitors, they need to be as close to the voltage lines as possible. So you can see, okay, you can see that we have two VCC pins here, so we need to have a capacitor near each one. So I will do the next one like this, press rat nest again, and align it. So, okay. And now let's do, and this would take more time if you needed to figure out this by yourself. But I'm showing you the solution basically. Oh, okay. And now I see that this won't fit. So because now I need to have this thing here, and now that it's not able to fit here. So what I'll do is just I'll rotate this once again, move it like this, and move the other one like this. Now they fit very well. So now you can also see that we have different types of components here. So some of the components have these green circles, and some of them have these red and sometimes blue squares, rectangles. And so these are through-hole components. So that means that in the PCB there is going to be a drilled hole with a piece of metal around it. And yeah, when you've ever seen a PCB, you know what it is. So you just insert a component there and solder around it. And here you have an SMD component. So SMD stands for surface mount device. So it's just on the surface. There is no hole. And you just have the component on top of the pads. So these are called pads. I think these are also called pads, but don't worry. So what next? We have these two and these two. So this is going to be the LED circuit. So we just place it somewhere here. And let me see how I did it. Yeah, so somewhat like this. This is the, I will align it, somewhat precise, and I will do this one. So this is the resistor, the current limiting resistor. On a normal board, you would normally have all the packages, you would like all the packages to be the same. So you would either have axial, so this is called axial. We've mentioned that many times when creating the schematic. So that just means that like this tubular shape. You've probably also seen that before. And you have these SMDs. So when you want a board to be very easily solderable, you want to have these large things. When you want the board to have better performance and be smaller and cost less, you want to have the SMDs. So that's why in, well, all the professional devices we have now, SMDs are used because it's cheaper, it's better, and easier for the manufacturers. I mean, for the ones who are soldering it.
And just something to add there, as we chose the components, like for example, the decoupling capacitors, you saw numbers like 06, 03, or 4, or 2, and these are just the inch indications of the dimensions of the sizes, like of the components. Like if you see the capacitors, they are pretty small. The of 04, 02, or 6, 03 is just an indication of the size we just chose.
Yeah, thanks. And now what? Let me see how exactly it's arranged so I don't mess it up. Yeah, this is perfectly fine. So this is the programming connector. So it's laying sideways, and here you would insert a programming console. So the last two components we need to add to the layout are, this is the pull-up resistor. So it goes, we press red nest again. We align it with this thing and with this line, and then here is the capacitor. So we probably didn't explain what this capacitor does. So it just it's like an electrical delay. So because the microcontroller is expecting the reset not to happen with a specific delay, and this capacitor makes the delay possible. So yeah, now we have everything neatly organized. I mean, it could definitely be better, but we can do that sometime later. So now I would draw the outline of the board, so we can have an outline. So I would also select the line tool down here. Some of you may have a smaller monitor, and you will need to press this thing to expand, and you will have it somewhere on this panel. So does everyone have the line tool and also the layout completed? Okay. So now, as you may have noticed, may have not, a lot of stuff here is based around the concept of layers. So you have many different layers in Eagle. You can see all of them, well, nearly all of them here. So you, for example, have the top layer, which is the top layer of copper. And then you have a bottom layer of copper. So if you've ever seen how PCB is made, it's also like a sandwich of layers. So you have the core of the PCB, which is just some silicon material, or yeah, something like that. It's called FR4. And on top of it, you have the copper printed. Then you have a thing which is called solder mask. I'm not sure where that is here, but solder mask is like a paint, which also stops electricity. And on top of that, you have just your graphics painted. So we'll get to that later. Now, you just need to select the layer 20 dimension, and that's the layer for, well, the outline or the dimension of the board. Yeah, why did I select move? So you set the width to 0 because the tools which are milling the board, like the CNC mill, are not precise because the drill bit have some width, but you want to have like a perfect model of where it should be drawn. So you don't want to have like a millimeter thick outline, because then you don't know what to expect. So normally it's put just at 0. And now you select the wire band to a right angle, so you have a right angle cut board. But the manufacturers can do anything. We could maybe even do like one of these. So you may need to play around with it a little because it jumps like differently, but we can do here a curved angle. Then if we switch here, there can be a right angle, and here we can do something like this. So this is like an angular cutout, something like that. So now when you complete the this, you just need to exit the line drawing mode. I just do that. I click on the most used thing. I click on move normally. I'm not sure whether you can do that with escape. That's what Sinan did before. I didn't use that method actually, but sure. So this is how the board looks like. So another cool feature you have in Eagle is this manufacturing panel. So does everyone have that in the free version of Eagle? Because I'm not sure whether that's available. Okay, great. Because I have a premium version, student version. So you just click on that, and rendering like this opens. So that's pretty nice. You can see how the board approximately would look like without the components. So now we can see that everything is pretty fine. Nothing is crossing over each other. And yeah, and you can also select the bottom side and see how the board would look from the bottom. So now, as I said, it could be better, but it's fine, and we can start routing the board. So what routing means is that you are, maybe I will move this just a bit in this direction, or maybe do like a half. Yeah, like this. So what routing means is that you are creating the wires in between the connections which need to be made. So you have different routing options here. So you have route, air wire. You can rip up, which is just deleting the routes. You have auto routing, which is not really good in any program. It's not even if you have more expensive programs for this, it won't really help you. Most times it's done manually. So for now, we are going to select the route airwire option. Now we have a lot of settings here. Maybe also what we could do is go in the tools, and you have DRC. I'll do that first. A DRC is like I'll show what DRC does later. We just now need to change the minimum drill size. So let's put that to 0.2 millimeters, because that's like the minimum hole that our manufacturer, which is JLC PCB, can do. Then we also go to masks and change the limit. This is just so that our holes are covered on the PCB, so then it's harder for them to short. So now we apply that, and yeah, now we can start the routing process. So you have this tool, and let's go through the settings. So you've already seen this bend style, so we can keep, this is the basic bend style, so like the angular we have here. And here you don't want to have zero width wires. For the signal ones, we can do, for example, 0.2 or 0.25, I can do that, millimeter wires. So, and we can start with that. So this needs to be connected, so you just click here, drag it like this, and connect it. And also for this, I would like a much smaller grid, so I'll go to 0.1 by default, and 0.05 can be the old version. So now you can move much more precisely. So then connect this. It's you can do this pretty fast because it's guiding you. So we can do this. So as I said here, it's good to be, the traces need to be uniform. So you can see that these are nearly symmetrical, maybe even completely symmetrical. We also connect this and this. So is this fine? Do you have this? Cool. So let's move on to the LED phase. The LED is actually going to pull some current, but not really much, so we can use the same trace width. So we put a trace here, and not here. We do not connect ground, so we do not connect ground yet. I will explain that later. Okay. Then we still need to connect these two. So I connect this one like this, and yeah, that's basically. I will first do the signal routes. Also, maybe many times I forgot, good practice is to do the power lines first. So because they are higher priority. So normally when you're designing a board, you would go from the highest priority routes to the lowest. So you start by RF route. So that's basically when you have a GPS antenna or something like this, then you do the power routes. And lastly, you do the signal routes. But since this is a very simple PCB, we do not really need to do that. But there is one conflict, or I can call it like this, that here you have the line crossing this thing. So we cannot go over it because it would short. We can do something like this or like this, but it's not good to do that. And this may seem like a big problem, but there is a very simple solution. So the board we are creating is has two layers. So 2 layers basically means it has 2 layers of copper specifically. So it has a layer of copper on the top and on the bottom. So we can just add, you can just put the trace on the other side of the board and we're fine. I'll show you how to do that. We will just do a smaller drill size here. So this is not wanting to go lower. Let me see why. So drill hole should be, yeah, that was not the correct setting. So this is the minimum drill setting. So again, you can go into the DRC, navigate to the minimum drill. I should have noticed that, and set this to 0.2 millimeters and apply. I'm not going to check if you have that because it's not really very important to have it set to 0.25, but it's better in this case. So because we don't need such a large via. So what a via is basically a hole going through the PCB, and it has metal in it. So when you have copper on one side, you can put the signal through the copper to the another side. So how to do that is just pressing the middle mouse button while routing. So I'm going to press that. And now we have a via. We can just place it here, or we can move it, but we can just place it here because here it's fine. So now here will be a hole, and now we can use the signal on the other side. So this is a signal on the other side is blue. Each layer has its own color, so you can navigate it. So let's draw the trace like this. So did everyone manage to get the trace on the other side successfully? Hey Samuel, what about you? Great. Let's go on. So this was done. You already know how to use a via. Now we will need it a bit later. Now we can just connect the power lines in here. So let's switch to the top bottom, to the top layer like this, and also switch the trace width to 0.5 because we are going to do the power lines and they need to be thicker because they are going to transfer more current. And then let's continue like we did before. So this and this one, and we can also let me think about that. Yeah, we are going to do a via. So now we have this finished, and yeah, we need to route the power from here to here, but also here and here. And the best way to do that from my point of view, at least right now, would be to do it on the other layer. So I'll just switch to bottom and wire it up. So something like this, and then go here. So we already have this connected. We just need to connect it here. So again, we are going to place a via. We are going to start here, but now we want to make the via larger because also there is going to be higher current. So I'll put the drill size to 0.35. With the via with the middle mouse button, add it here, and just route this. And this is basically the end of the manual routing process. So is everyone at this stage?
I'm sorry to interrupt. I just want to add something about VIAs and SMD components. You might have guessed, but I will just say it anyways. As you can see, the SMD component near the VCC, like the capacitor in the middle, the blue line goes kind of through the component. And that's totally fine because, like Jakub said, the SMD is on top of the PCB and the blue line is below it. You just have to watch out for the green VIAs because there you cannot route it just through. Then you do an electrical connection. I think that goes without saying, but I just wanted to add that.
Yeah. You can route it through when it's the same signal, like here. That's totally fine. But if I would want to do this, then it won't even let me because it's smart. So now you can see, I said the manual routing process is over, but you can see that all of these ground signals are still not wired. So we can do that either manually, like we did with these ones, but that's not the standard process. So how to do that better is to do a ground plane. So a ground plane is basically a large surface filled with ground copper. So I'm going to do that now. Set the grid again to 1 millimeter and select the polygon tool. So with the polygon tool, you cannot mess with the polygon tool. You need to create a polygon on the first try. So you should all know what's a polygon. A polygon is just the shape from polylines. So it should have some width. So let's set it to 0.25. We also have some other settings here. Thermals on. Yeah, this is fine. And we have it set to the top layer. So top layer 0.25 hatches on. So we start copying the shape of the outline. So we start here, we go here, and now we want to select this curved thing again. Isn't there a disentanglement function, a similar program like Eagle? I'm not sure. Like, you mean the Ratness tool? If that's in different programs? Yeah. I mean, like, the junctions are eliminated. Well, sometimes you cannot eliminate them, because imagine that there would be 10 different components laying over each other, and sometimes you just don't have a mathematical way, or geometrical way rather, to eliminate the crossings, because all the lines have some width, and when you imagine, sometimes you just cannot go around. So what you do when you cannot go around, you just add another layer. So now we have 2 layers, but you can have another layer in the middle, but you cannot do that automatically. I hope that that's the answer. Auto board layout tool. Yeah, maybe that was the question. Yeah, I don't think that exists. But also the Ratness tool is like a specialty of Eagle. I work the different programs, and most of them do this automatically. But not really a big deal. Let's wait for the question. Sorry to leave the other people hanging with the polygon. Okay, maybe we can continue on with the polygon or return to the question a bit later. So you do this, you go up, and here you go with the angular tool once again and go down. So now be prepared for a prompt. You get a prompt which asks for the signal name. So you have only one try at this, put G and D there and enter. So now you have this nice shape drawn around the board. And now the magic happens when you press the redness tool. So now there's a rendering. Now this all red red sea appeared. So now you can see that the ground is everywhere else than other signals are. So it's basically going around each signal that is not ground. And when a signal is ground, it's connected to it this way. So this is called thermal, and it basically just makes the soldering process easier. So we have this, and we just need to do that to the other side as well. So we just select bottom, and we do the same. So that shouldn't be a problem. Again, the circular tool, go here, the angular tool here, and the home position. And again, we do G and D. Now, this is an equals redness. Now, this is great because now you have both sides covered with ground. So you don't need to route ground anymore. But there's also an issue because the ground is separated. So you have two different panels of ground, and two different sheets of metal not connected in many spaces is not good. So it can work as an antenna, as a capacitor, and it can have adverse effects. Also, when there is a component that is taking some power, sometimes the electricity needs to go through long paths. So, for example, when you have ground here, and so this LED and this resistor are consuming power, so they need ground and voltage. So the voltage, they have voltage here, and they have the ground here. But in order for the ground to work, it needs to be connected with the power supply ground. So that's here. Now this is pretty optimal, but in some cases you have the power needs to go around the board, so some distance on one side and some distance on the other side. But also only the fact itself that you have these layers not connected, create some problems. So we are going to resolve that, but by adding some VS. I'm not sure how these are called specifically, but just normal VS. So select the VIA tool. We already used VS before, but now we want to do them. We want to add the VS separately. So we are using a large 5mm grid, and add the VS here like this. We can set their size to 0.25. Maybe 5mm, not the right size. Maybe do 2. No, 4. What looks good? Again, this is a thing of OCD and symmetry and stuff. All of these different factors. And sometimes when you are doing RF, mainly you need to have a special way for them to be arranged. But most times, just having it like this is okay. So do this, just add them like on the grid. That should be pretty easy. And yeah, sometimes you have some spaces where, okay, it can go here, here, and here. Sometimes you have some spaces where it doesn't fit, so we do a smaller grid, and we just put it here, put it here, and here. Right, so we have all of our vias. Now we press the redness tool, and you can see that all of them are disconnected. So now we want to connect them to ground. So there are some ways, multiple ways you can do that. You can either, well, firstly, this is a selection filter. So when you have a lot of layers, you can click somewhere, it can select the thing on the other layer, something you didn't want. So we can just press on VS, click on VS, and now we'll only select the VS. Okay, does everyone have the VS placed? Good. So we have the VS, and this, well, the most straightforward way to connect the VIA somewhere is to just rename it. So we click here and we type in GND. We also copy that, and it just connects to both sides. But clicking this out for each of these would be really hard. So we can do a little. We can use this trick. I'm not sure. Yeah, something. You can select it with the group tool. And now, yeah. Now will be. Okay, I used this a long time ago, so just select it and go to okay, I'm not really sure how to do it now, so it's not, yeah.
I think, I don't know if that's possible in Eagle, if you place a VIA and rename it to GND, and then you place many VIAs. I think they all share the same name, or you could use the group tool and control click every VIA if it's needed.
Okay.
Like, I think if you place one VIA, name it ground, and then place the other ones again, I think
this is one of the, well, this is one of the things I really hate about Eagle. Okay, this maybe we'll do it now. Okay, yeah, we will need to learn this. I will need to learn this, but for now, just clip it to your clipboard, and it's reasonably fast. I have it keybinded on my mouse, but I will give you some time to do that because this is a really stupid process. So I'll give you some more time to do that. When you are done, just type in the chat.
And don't rename the connected vias that were used.
Yeah.
Rename the ground.
Yeah, this was stupid, but sure. You don't really need to have all of them connected. It won't break anything, but when you already have them placed. Okay, Veronica has it.
Yeah, and this simple schematic, like these stitching vias, are not that important. Like for this board, for example.
Yeah. Now, yeah, we are going into. We don't have much more time left, so let's do the last thing we will do, and then we will look at the. Okay, so don't work with the vias anymore. This is not really important. You can finish it sometime later. But now the last tool we will show you today is okay. Thanks. So the last tool I will show you now is the text tool. So we can just add a text. So anything like I first see something. It's on you. And then, well, you can place it like this here. Yeah, that's fine. But now you see that Eagle really hates this and puts. When Eagle does red polygons like this, that's a bad sign, and that's because we put it to the wrong layer. Yeah, this was selected. For those of you who have the via selected, you need to either do top or press this all, and now you can work with the whole board again. It's probably even better. It's not selecting, so okay, maybe try it with the group tool, because when this cross is red and the whole thing is red too, it's hard to see. So now we can just do info and change its layer to, well, let's say top names. So that's a layer on the silk screen. So a silk screen is basically just, which I explained earlier, it's a layer where texts and images are printed on the board. Now it's fine, we need to hit red nest again, so it clears this area, or it puts copper to this area. And now when you click the board preview, it needs to render, but now you can see a lot of nice stuff. So this is the board from the bottom. You can see traces, the copper, the vias, everything. And when you go to the top, you can see some other cool stuff. So you can see connector, the caps, the crystal, everything. Everything is here, everything is connected. You can do like a check, because sometimes you cannot see it on the board view, and here you can notice that something is misaligned or not shorting really, but just close to one another too much. But this should be fine. Well, also good practice. So this is basically the finished PCB. You can save it. Yeah, you can save it. I already have it as a file, so it says for me, for you, maybe you'll have a prompt, maybe not. But before actually ordering this, you will need to check it. So you have DRC. DRC stands for design rule check. We already used this for the settings, but we didn't actually check it. So let's press check. And what do we have? And it probably just shows up in another window or doesn't work at all. So check again. Oh, no errors. So yeah, that's really cool. This is one of the first. This doesn't happen a lot because when I do some complicated PCBs, it's always like, even when you do this a lot, you have like 50 errors when you run the DRC check. So is everyone else so lucky, or do you have some errors? Oh, nice. Okay, same. Great. So the last thing to do is open the CAM processor. So open that, and you will see basically the layers of the board. So this is what I talked about. So this is the top copper layer. So when the board is made, this is how the copper on the top will look like. This is how the copper on the bottom will look like. This is the board, so how the board shape will look like. This is the solder mask. So the solder mask is so you don't really need to worry about that much at this stage. So here you have solder paste, and lastly there is silk screen, so the stuff that's printed. You can process it here, maybe, but since we are not changing any settings, you can just close this and use the second thing, which is just like a quick export function. And you just create this, click OK, and I'll put it in the downloads folder. And save this. Now it's here. So everyone should have this. Do you have it? Okay, so we are already 7 minutes over the limit, but if you want, I can still show you how to order a board, or how to upload it and set the settings to get the board to you, actually. Okay, yes, sure. So let me open another browser. Yeah. So we have many different PCB manufacturers out there. You most certainly have in your country, but if you don't live in China, they are going to be very expensive. So you can pay hundreds of euros, so thousands for a single board, or not a single board, but a couple of prototype boards, because the prototype costs are high. That's why we all order from China, and there are many Chinese sellers. So we are sponsored by, or we got a coupon from PCBWay, and we are going to use that soon. But I don't have much experience with PCBWay yet. That's why I will show you the JLC. JLC ordering, or maybe I can show you the PCBWay and JLC too. It's very similar, but JLC has a preview. So let's do both. So they look kind of similar. On both of them, you have the homepage and you have this quote buttons. So you press quote now on both, and you will know at least how to use both of them. Just a second. Okay, so here you just upload the file, and here you do the same. Okay, I'm not even sure whether you are following along. You don't really need to at this point. But if you are, do you have this? Okay, right. So both of these are similar. So yeah, both of them have a preview. You can see this is very similar to what we had in Eagle. And here you have some auto-detected parameters. So you have the size, quantity, layers. So here, as you can see, PCBWay can do 10 layers. JLC can do 6 layers. So yeah, let's go through this one first. So this is fine. Select how much you want. Let's say we want 10 of these. We want them to be 1 millimeter thick because 1.6 is the standard. I like to use 1 for generic small stuff, and for Picoballoons we use 0.6 because they are the lightest, and 0.4 are much more expensive. So let's do 1. And yeah, the green is very basic. You maybe have seen a question in the chat. So how do you receive the signals? Well, yeah. So you have a FTDI console. So FTDI console, no cable, and it looks like this. Like this. No, it's the most relevant image is in Wish, but this seems to be the only legitimate Wish product. But sure, it looks like this, and you just this should have the same layout. Does GND, yeah, and you just insert these 6 pins into a connector that would be here. So these 6 pins, there would be like a header connector. You connect that there, and you can program it that way. I hope that's what you're looking for. Also, we can do a panel, so that means that the PCBs are not just a bunch of PCBs, but they would be connected to each other in a panel. And yeah, the color is something which you can change, so you can have green, blue, black, stuff like that. And yeah, the prices are also pretty similar. You can also see the calculated weight. That's very important for Picoballoons. Yeah, that's basically it. So now you should be able to. Oh, if I wanted to have a hole in the PCB for the screw, how would I do that? Sure, I'll show.
Jacob, I want to remind you that that we should come to an end.
Yeah. So I'll just resolve this last question. Hole is very simple here. Nuvia, you select the hole, select the size. You want to do 1 millimeter hole. You put the hole here, for example, and rat nest, and we have a hole. When it blows up, you should have a hole. Is that fine? Great. So yeah, I hope that everyone understood everything, and thanks to Sinan to doing the first segment with schematics. And if you want to learn more about the project, you can visit our website, which I will put in the chat, or it's here. You also see my screen. That's fine. Here's it. Okay. Yeah. Okay. So if there are no more questions, comments, anything, then that's it today from me.
Thank you very much for listening, from me too. And yeah, from me also, have a nice day, and thanks for listening.
Yeah, thank you very much for the...
There is still some activity in the chat.
Thank you very much for the presentation and the good workshop. I think the people who listened learned something to how to invent something with Eagle. I think they had enjoyed the workshop. Thank you very much.
Yeah, thank you too. Let's just
thank you.
Yeah. So have a nice weekend, right? And bye.